Tonight, we're going to talk about something that's going to fundamentally change how you see our place in the universe. For your entire life, you've thought we lived in a normal region of space, just another spot in the cosmos. Average. Typical. Nothing special. But here's what scientists recently discovered. We don't. We've been living inside one of the largest empty regions in the entire universe this whole time. A cosmic void so vast that it's affecting everything we see when we look out at the stars. And we only just figured it out. And by the end of tonight, you're going to understand what this void is, how it's been hiding in plain sight, and what it means for our understanding of the universe itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what you think you know about the universe. When you look up at the night sky, you see stars scattered across the darkness, thousands of them, visible to the naked eye. Through telescopes, you see millions more, galaxies stretching in every direction, clusters of galaxies bound together by gravity, superclusters containing thousands of galaxies. The universe seems full, packed with matter and light and structure. And in a sense, it is. But here's what most people don't realize. The universe isn't distributed evenly. Matter doesn't spread out like a smooth fog filling all of space uniformly. Instead, it clusters. It forms patterns. Galaxies group together into clusters. Clusters group together into superclusters. Superclusters stretch along filaments, forming what astronomers call the cosmic web. And between these filaments, between these concentrations of matter, there's mostly nothing. Voids. Enormous empty regions where very few galaxies exist. These voids aren't small. They're not little gaps between galaxies. They're massive structures, hundreds of millions of light years across. Regions of space where the density of matter is so low that if you were somehow placed in the center of one, you'd see almost nothing when you looked out. No nearby galaxies. No bright stars. Just darkness, stretching in every direction for hundreds of millions of light years. The nearest significant structure would be so far away it would appear as barely a faint smudge even through powerful telescopes. For decades, astronomers knew these voids existed. They'd mapped them, measured them, studied their properties. Voids are a natural consequence of how the universe evolved. In the very early universe, shortly after the Big Bang, matter was distributed almost uniformly. Almost, but not quite. There were tiny fluctuations in density. Some regions were slightly denser than average. Others were slightly less dense. These differences were incredibly small, just 1 part in 100,000. But over billions of years, gravity amplified these fluctuations. Dense regions attracted more matter, becoming denser still. Less dense regions lost matter to their surroundings, becoming even emptier. The denser regions eventually became the galaxy clusters and superclusters we see today. The less dense regions became voids. By now, billions of years after the Big Bang, the contrast is extreme. The densest regions contain thousands of galaxies, packed relatively close together. The voids contain almost nothing. This process created the cosmic web, a vast network of filaments and walls made of galaxies, surrounding enormous, empty voids. It's one of the most striking features of the universe when you map it out at the largest scales. And Earth sits somewhere in this structure. The question is, where? For a long time, astronomers assumed we lived in a fairly typical location. Not in the densest regions, not in the emptiest voids, but somewhere in between. A normal spot on one of the filaments that make up the cosmic web. This assumption made sense. If you pick a random location in the universe, odds are you'll land somewhere on a filament rather than in a void, simply because filaments make up more of the volume than the extremely dense clusters. Voids, despite being enormous, actually occupy most of the universe's total volume. About 80% of all space is void. But galaxy formation happens in the dense regions. So most galaxies, including ours, should be on filaments rather than floating alone in voids. That was the thinking anyway. But then, astronomers started noticing something strange. When they measured the expansion rate of the universe from our location, they kept getting a number that didn't quite match what they expected based on observations from other methods. This discrepancy is called the Hubble tension. It's one of the biggest unsolved problems in cosmology right now. The Hubble constant describes how fast the universe is expanding. It tells you how quickly distant galaxies are moving away from us. When you measure this expansion rate using nearby objects, you get one number. When you calculate it from observations of the early universe, specifically the cosmic microwave background radiation left over from the Big Bang, you get a different number. The two numbers don't match. They're off by about 9%. That might not sound like much, but in physics, a 9% discrepancy is enormous. It's not measurement error. Both measurements are precise and have been checked and rechecked by multiple independent teams using different methods. The numbers simply don't agree. This suggests something is wrong with our understanding of how the universe works. Either our measurements are being affected by something we haven't accounted for, or our theoretical models are incomplete. And one possible explanation is that we're living in a void. Here's how a void could create this discrepancy. The Hubble constant isn't actually constant everywhere in the universe. It varies depending on where you are. In denser regions, where there's more matter, gravity slows down the expansion slightly. In voids, where there's less matter, the expansion happens faster. If we're living in a void, the expansion rate we measure from our location would be higher than the average expansion rate of the universe as a whole. This could explain why our local measurements of the Hubble constant are higher than what we calculate from the cosmic microwave background, which represents the average expansion rate across the entire observable universe. The idea that we might live in a void isn't new. Astronomers have been proposing this as a possible solution to the Hubble tension for years. But for a long time, it was considered unlikely. Our location didn't seem particularly empty. We're in the Milky Way, which is part of the Local Group, a small cluster of galaxies, including Andromeda and about 50 smaller dwarf galaxies. The Local Group is part of the Virgo supercluster, which contains thousands of galaxies, and the Virgo supercluster is part of an even larger structure called Laniakea, which contains about 100,000 galaxies. That doesn't sound like a void. That sounds like a fairly well-populated region of space. But here's what astronomers recently realized. We're not in the deepest part of the void. We're on the edge. In 2014, astronomers mapped out a structure they called the KBC Void. KBC stands for the three astronomers who studied it extensively: Ryan Keenan, Amy Barger, and Lennox Cowie. This void is enormous. It stretches about 2 billion light-years across. That's roughly 2% of the diameter of the observable universe. For comparison, the Milky Way is 100,000 light-years across. The KBC Void is 20,000 times larger. If you could somehow travel at the speed of light, it would take you 100,000 years to cross the Milky Way from edge to edge. It would take you 2 billion years to cross the KBC Void. Inside this void, the average density of galaxies is about 20% lower than the cosmic average. That might not sound like a huge difference, but when you're talking about a region 2 billion light-years across, that missing matter adds up. There are hundreds of millions of galaxies fewer inside the void than there would be if matter were distributed uniformly. Now, here's the critical discovery. Our Milky Way galaxy sits near the edge of this void. Not at the center, where the emptiness is most extreme, but in the outer regions, where the void gradually transitions back to normal cosmic density. We're in a position where we can see both the void stretching out in one direction and the denser cosmic web structures in the other directions. This location has profound implications. If we're on the edge of a void, then when we look out in certain directions, we're looking through the void toward the denser regions beyond. And when we look in other directions, we're looking into the void itself, toward the nearly empty center. The expansion rate of space is different in these two directions. The void expands faster. The denser regions expand slower. This creates an asymmetry in what we observe. It affects our measurements of the Hubble constant because we're not sampling a representative region of space. We're sampling a biased region, skewed toward lower density. The implications of this discovery are still being worked out. Some astronomers think it could explain the Hubble tension completely. If we account for the fact that we're in a void and adjust our measurements accordingly, the local expansion rate might match the cosmic average after all. Other astronomers are more cautious. They point out that even accounting for the void, there's still some discrepancy. The void helps, but it might not solve the entire problem. There might be other factors at play as well. But one thing is clear. We're not in a typical location. We're in a void. And that changes how we need to interpret everything we observe. Let's talk about what it means to be in a void. First, it's important to understand that voids aren't completely empty. They're called voids because they contain far fewer galaxies than average, but they're not a perfect vacuum. There are still some galaxies scattered throughout, even the largest voids, just very few of them. In a typical region of space, you might have a galaxy cluster every few million light-years. In a void, you might have to travel 100 million light-years before you encounter another significant concentration of galaxies. The voids aren't completely empty of matter either. There's still gas in voids. Primarily hydrogen and helium, the lightest elements created shortly after the Big Bang. This gas is incredibly diffuse, with densities far below what exists between galaxies in normal regions of space. But it's there, filling the void like an extremely thin fog. There's also dark matter in voids. Dark matter is the mysterious substance that makes up about 85% of all matter in the universe. We can't see it directly because it doesn't emit, absorb, or reflect light, but we know it exists because of its gravitational effects. Dark matter is what holds galaxies together and shapes the large-scale structure of the universe. In voids, there's less dark matter than in denser regions, but it's still present. The gravitational field of this dark matter affects how galaxies move and how light travels through the void. So voids aren't truly empty. They're just far less dense than the rest of the universe. But from our perspective, observing from inside a void, the effect is significant. When we look out at the universe, we're seeing it through a lens that's not quite representative of the cosmos as a whole. It's like trying to understand what Earth's surface is like by only sampling the Sahara Desert. You'd get a skewed picture. Too dry, too hot, too empty. You'd miss the forests, the oceans, the polar ice caps. Similarly, observing from inside a void gives us a skewed picture of the universe's structure and expansion rate. We see less matter, faster expansion, and a slightly different cosmic landscape than what an observer in a denser region would see. This raises an interesting philosophical question. How much does our location matter? In principle, the laws of physics are the same everywhere. The speed of light, the strength of gravity, the behavior of subatomic particles, all of this is universal. It doesn't matter whether you're in a void or in a galaxy cluster, but your observations depend on your location. The universe looks different from different vantage points. For most of human history, we assumed we were at the center of everything. First, we thought Earth was the center of the universe, with everything else revolving around us. Then we learned Earth orbits the Sun. Then we learned the Sun is just one star among billions in the Milky Way. Then we learned the Milky Way is just one galaxy among trillions. Each step pushed us further from the center, from any notion that we occupy a special or privileged position. The Copernican principle, named after the astronomer Nicolaus Copernicus, who first proposed that Earth orbits the Sun rather than the other way around, has become a cornerstone of modern cosmology. It states that we don't occupy a special place in the universe. Earth isn't special. The Sun isn't special. The Milky Way isn't special. Our location is typical, average, unremarkable. This principle has guided astronomy for centuries. It's one of the fundamental assumptions underlying our models of the universe. But if we're in a void, does that violate the Copernican principle? Are we in a special location after all? Not necessarily. Voids make up about 80% of the universe's volume. Most of space is void. So being in a void isn't particularly special. It's actually fairly typical. What might be special is being near the edge of a void rather than in the center or in a dense region. Edges are transition zones, and transition zones make up less volume than either the voids themselves or the dense filaments. But even this isn't necessarily a violation of the Copernican principle. Every void has an edge. There are countless voids throughout the universe, each with their own edges. Being on the edge of one of them isn't particularly improbable. Still, there's something unsettling about this discovery. For decades, we've been measuring the universe from our location, assuming we're in a typical spot. Now we're learning that our location might be biasing our measurements. Everything we see, every observation we make about the large-scale structure of the universe is filtered through our position on the edge of this void. It's like trying to measure the average height of humans, but you're standing in a country where people are shorter than average. Your sample is biased, even if you don't realize it. You might conclude that humans are shorter than they actually are on average. Similarly, measuring the universe from inside a void might lead us to incorrect conclusions about the universe's overall properties. This is why the discovery is so important. It forces us to reconsider all our measurements and observations. It forces us to ask whether what we've been seeing is truly representative of the universe as a whole, or just representative of our local neighborhood. Let's talk about how astronomers actually discovered and mapped the KBC Void. It wasn't easy. Voids are defined by an absence of galaxies, and measuring absence is tricky. You need to map out the positions of millions of galaxies in 3 dimensions, not just their positions on the sky, but also their distances from us. Only then can you see the patterns of clustering and the empty regions between them. This requires 2 things. First, you need a comprehensive survey of galaxies. You need to observe as many galaxies as possible across as much of the sky as possible. Second, you need distance measurements for all those galaxies. Just knowing where a galaxy appears in the sky isn't enough. You need to know how far away it is to map its true position in 3-dimensional space. Distance measurements for galaxies come from redshift. When light travels through expanding space, its wavelength gets stretched. Light from distant galaxies is shifted toward longer, redder wavelengths. This is called cosmological redshift. The farther away a galaxy is, the faster space is expanding between us and that galaxy, and the more its light is redshifted. By measuring the redshift of a galaxy's light, astronomers can calculate its distance. This isn't perfect. Redshift tells you how fast a galaxy is moving away from you, and most of that motion comes from the expansion of space. But galaxies also have their own motion through space, called peculiar velocity. A galaxy might be moving toward us or away from us, independently of the expansion. This peculiar velocity adds or subtracts from the redshift, creating uncertainty in the distance measurement. For very distant galaxies, billions of light-years away, peculiar velocity is negligible compared to the expansion velocity. But for nearby galaxies, within a few 100 million light-years, peculiar velocity can significantly affect the measurement. This makes mapping the local structure of the universe challenging. Despite these challenges, astronomers have conducted several massive galaxy surveys over the past few decades. The Sloan Digital Sky Survey, which started in 2000, mapped the positions and redshifts of millions of galaxies. The 2-degree Field Galaxy Redshift Survey did similar work. More recently, surveys like the DESI survey, the Dark Energy Spectroscopic Instrument, are mapping tens of millions of galaxies with unprecedented precision. These surveys revealed the cosmic web in incredible detail. When you plot the positions of millions of galaxies in 3-dimensional space, the structure jumps out at you. Filaments of galaxies stretching across hundreds of millions of light-years. Walls of galaxies forming sheet-like structures, and voids. Enormous empty regions where very few galaxies exist. The KBC Void showed up clearly in these maps. It's one of the largest voids in the local universe, and its extent is well defined. Astronomers measured the density of galaxies inside the void compared to the density outside, and found that the void is indeed significantly underdense. About 20 to 30% fewer galaxies than you'd expect if matter were distributed uniformly. They also measured the Milky Way's position relative to the void. We're not at the center. We're roughly 700 million light-years from the center, which places us in the outer regions of the void. We're in a transition zone where the void's low density gradually increases toward the normal cosmic density of the surrounding regions. This position is important. If we were at the center of the void, the effect on our observations would be more dramatic. The expansion rate in every direction would be unusually high. But because we're on the edge, the effect is more subtle. Looking in some directions, we see through relatively normal regions of space. Looking in other directions, we see through the void. This creates an asymmetry in our measurements, but it's not as extreme as it would be if we were dead center. Now, let's talk about how being in this void affects specific observations. Start with the Hubble constant. The Hubble constant relates a galaxy's distance to its velocity. The farther away a galaxy is, the faster it's moving away from us due to the expansion of space. The Hubble constant is the proportionality factor between distance and velocity. To measure the Hubble constant, astronomers observe distant objects with known intrinsic brightness, called standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate its distance. Then you measure its redshift to determine its velocity. Distance and velocity give you the Hubble constant. One of the most reliable standard candles is a type of exploding star called a Type Ia supernova. These supernovae all reach approximately the same peak brightness when they explode. By measuring how bright a Type Ia supernova appears from Earth, you can calculate how far away it is. Astronomers have used Type Ia supernovae to measure the Hubble constant from local objects within a few 100 million light-years of us. These local measurements consistently give a value of about 45 miles per second per megaparsec. That means, for every megaparsec of distance, about 3.26 million light-years. A galaxy's velocity increases by 45 miles per second due to the expansion of space. But when astronomers calculate the Hubble constant from the cosmic microwave background, the radiation left over from the Big Bang, they get a different number, about 42 miles per second per megaparsec. 3 miles per second per megaparsec might not sound like a big difference, but it represents about 9%, and it's persistent across multiple independent measurements using different methods. This is the Hubble tension. If we're in a void, our local measurements might be biased. The expansion rate inside a void is faster than the average expansion rate of the universe. So, when we measure the Hubble constant using nearby objects, we're actually measuring the expansion rate of the void, not the average expansion rate of the universe. If you account for the void's effect, the local measurement might come down closer to the cosmic microwave background value. Some recent studies have tried to quantify this effect. They've modeled how being in a void would affect our measurements and calculated how much of the Hubble tension could be explained by the void. The results are promising, but not conclusive. The void can account for some of the discrepancy, perhaps 1 to 2 miles per second per megaparsec, but probably not all of it. There's still some tension remaining, even after accounting for the void. This suggests the void is part of the answer, but there might be other factors involved as well. Maybe our understanding of dark energy, the mysterious force causing the universe's expansion to accelerate, needs refinement. Maybe there are other systematic uncertainties in the measurements that haven't been fully accounted for. Or maybe the void is larger or more underdense than current estimates suggest, and its effect is actually stronger than we've calculated. The truth is, we don't know yet. This is an active area of research. New data from surveys like DESI will help refine our measurements of the void's properties and our position within it. And as we get better measurements, we'll be able to test whether the void fully explains the Hubble tension or whether something deeper is going on. Being in a void also affects other observations. For instance, the distribution of galaxies we see around us is affected by the void. When we look toward the center of the void, we see fewer galaxies than we'd see if we were in a normal region of space. When we look away from the void, toward denser regions, we see more galaxies. This creates an asymmetry in the sky. Some directions look emptier, some look denser. For most purposes, this doesn't matter. Cosmologists are interested in the average properties of the universe at the largest scales, and local variations like voids don't affect the big picture. But for precision measurements, local variations can introduce bias. If you're trying to measure the large-scale distribution of matter in the universe, you need to account for the fact that your vantage point might not be representative. Another effect involves something called the integrated Sachs-Wolf effect. This is a subtle effect where light from the cosmic microwave background gets slightly boosted or diminished in energy as it travels through regions of space where the gravitational potential is changing. In a void, the gravitational potential is weaker and changing differently than in denser regions. This affects the cosmic microwave background light passing through the void in measurable ways. Astronomers have detected the integrated Sachs-Wolf effect from various voids throughout the universe, including the KBC Void. The signal is faint, but it's there. It provides independent confirmation that the void exists and that its gravitational properties differ from the surrounding space. So, being in a void leaves imprints on multiple different types of observations. The Hubble constant is affected. The galaxy distribution is affected. The cosmic microwave background is affected. All of these provide clues that we're not in a typical location, and all of them need to be accounted for when we try to measure universal properties of the cosmos. Let's zoom out and think about what this means for our understanding of the universe. For decades, cosmology has been built on the assumption that the universe is homogeneous and isotropic at large scales. Homogeneous means uniform. If you look at large enough volumes of space, they all contain roughly the same amount of matter and have the same properties. Isotropic means the same in all directions. The universe looks the same no matter which direction you look. These assumptions are part of the cosmological principle, an extension of the Copernican principle. They've been incredibly successful. They form the foundation of the Big Bang model and the Lambda CDM model, our current best description of how the universe works. But they're approximations. At small scales, the universe is definitely not homogeneous. Planets, stars, galaxies, clusters, voids, all of these represent significant departures from uniformity. The question is, at what scale does the universe become sufficiently uniform that we can treat it as homogeneous for the purposes of cosmological models? The standard answer has been about 300 to 500 million light-years. If you average over volumes of that size, local structures like galaxy clusters and voids smooth out. You get a fairly uniform distribution of matter. But the KBC Void is 2 billion light-years across. That's larger than the scale at which the universe is supposed to become homogeneous. If we're in a structure this large, and if it's affecting our observations, then maybe the universe doesn't become truly homogeneous until even larger scales. Maybe the assumption of homogeneity breaks down more than we thought. This doesn't invalidate the Big Bang model or Lambda CDM. Those models are still correct at the largest scales. But it does mean we need to be more careful about how we apply them to our local measurements. We can't assume our local neighborhood is representative of the universe as a whole if we're sitting in a 2 billion light-year wide void. Some astronomers have suggested that the KBC Void might actually be even larger than 2 billion light-years. The measurements are uncertain, especially at the edges where the void gradually transitions to normal density. If the void extends farther than current estimates, its effect on our observations would be correspondingly larger. There's also the question of whether the KBC Void is unusual. Is it an outlier, one of the largest voids in the entire universe? Or are there many voids this size scattered throughout the cosmos? If voids this large are common, then being in one isn't particularly special. It's just a consequence of the universe's large-scale structure. Current surveys suggest voids of this size are rare, but not unique. There are other voids throughout the universe that approach or exceed 2 billion light-years in diameter. The Eridanus supervoid is another enormous underdense region, discovered through its effect on the cosmic microwave background. The Boats void, discovered in the 1980s, is about 330 million light-years across, smaller than the KBC Void, but still substantial. These voids are all part of the cosmic web, the large-scale structure that emerged from tiny fluctuations in the early universe. So we're not in a completely unique location. We're in a rare, but not impossible location. A position that requires us to be careful about how we interpret our observations. There's one more important aspect of being in a void that's worth discussing: the future. The universe is expanding, and the expansion is accelerating due to dark energy. In denser regions, gravity works to slow the expansion slightly. Clusters and superclusters are gravitationally bound, meaning the expansion doesn't pull them apart. They hold together even as the space around them expands. But in voids, there's less matter, and therefore less gravity to counteract the expansion. Voids expand faster than denser regions. Over billions of years, this means voids grow. They get emptier as the few galaxies inside them move apart, and as the expansion carries them toward the void's edges. The KBC Void is growing. Billions of years from now, it will be even larger and even emptier than it is today. The Milky Way, sitting on the edge of the void, will see this growth. The void will expand in one direction, while the denser regions of Laniakea expand less rapidly in the other directions. This creates an asymmetric expansion pattern around us. Eventually, in the far future, trillions of years from now, the accelerating expansion of the universe will cause even-bound structures like galaxy clusters to begin stretching apart. The universe will become increasingly empty as galaxies move beyond each other's cosmic horizons, unreachable even at the speed of light. But that's a story for another time. For now, the important point is that being in a void affects not just our present observations, but also how we'll observe the universe's evolution in the future. Let's bring this back to the human perspective. What does it mean for us, for humanity, to discover we're living in a void? On one level, it doesn't change anything about our daily lives. The void is so large, and its effects so subtle, that you'd never notice it without precise astronomical measurements. The sun still rises and sets. The moon still orbits Earth. Life goes on exactly as before. But, on another level, it's a profound shift in perspective. We thought we understood our place in the universe. We thought we were in a typical location, observing a representative slice of the cosmos. Now we know we're in a statistical outlier, a region of space that's emptier than average. It's a reminder of how much we still don't know. Even basic facts about our cosmic neighborhood, facts that affect every observation we make, have only been discovered in the past decade. How many other aspects of the universe are we misunderstanding because of biases we haven't yet identified? This discovery also highlights the importance of continued observation and measurement. We didn't discover the KBC Void through pure theory. We discovered it by painstakingly mapping the positions of millions of galaxies, measuring their distances, and looking for patterns in the data. It took decades of work by thousands of astronomers using some of the most advanced telescopes in the world. And even now, our understanding is incomplete. We're still refining our measurements of the void's size and density. We're still debating how much it affects our observations. We're still trying to determine whether it can fully explain the Hubble tension or whether other factors are at play. The scientific process is ongoing. Each new piece of data helps us understand a little more, but also reveals new questions we hadn't thought to ask. There's something humbling about this. For all our technological advancement, for all our sophisticated theories and equations, we're still fundamentally limited by our perspective. We observe the universe from one particular location at one particular time. We can't step outside the universe and view it from an external vantage point. Everything we know comes from light that's traveled across space to reach us. We're like inhabitants of a small island trying to map the entire ocean by watching the patterns of waves lapping at our shores. We can learn a lot. We can make accurate maps. We can predict how the ocean behaves. But our view is inherently limited by where we stand. Being in a void is part of that limitation. It's a factor we need to account for, a bias we need to correct, if we want to understand the universe as it truly is, rather than just as it appears from our location. And yet, despite this limitation, we've achieved something remarkable. We've figured out that we're in a void. We've mapped its extent. We've measured its properties. We've calculated how it affects our observations. We've taken our biased perspective and accounted for the bias, at least partially. That's an extraordinary accomplishment. It demonstrates the power of science to overcome even fundamental limitations. As we move forward, new surveys and observations will continue to refine our understanding. The DESI survey, which started collecting data in 2021, will map tens of millions of galaxies. The Vera C. Rubin Observatory, expected to begin operations soon, will survey the entire visible sky every few nights, creating an unprecedented three-dimensional map of the universe. The Nancy Grace Roman Space Telescope, planned for launch later this decade, will provide even deeper views of distant galaxies. These projects will help us better characterize the KBC Void and our position within it. They'll also reveal other structures we haven't yet discovered, other voids and walls and filaments that make up the cosmic web. With each new discovery, our picture of the universe becomes more complete and more nuanced. We're living in a golden age of cosmology. The next few decades will bring insights that would have seemed impossible just a generation ago. And one of those insights is this: we're in a void. We've been in a void this entire time. It's been hiding in plain sight, literally surrounding us, affecting everything we see, and we only just figured it out. This is the nature of scientific discovery. The universe doesn't reveal its secrets easily. We have to work for them. We have to build telescopes and satellites and supercomputers. We have to collect data and analyze it carefully. We have to question our assumptions and test our theories against observation. And sometimes, after decades of work, we discover something fundamental about our place in the cosmos that nobody suspected. We've been living inside one of the largest empty regions in the entire universe. A void so vast, it affects the expansion rate of space itself. And this discovery changes how we interpret every observation we've ever made about the universe's large-scale structure. It's a reminder that the universe is full of surprises, that even when we think we understand something, there's always more to learn. That our perspective, limited as it is, can still uncover profound truths about reality. So the next time you look up at the night sky and see those distant stars and galaxies, remember what you've learned tonight. You're not looking out at the universe from a typical location. You're looking out from the edge of a void, an enormous empty region stretching nearly 1 billion light-years in certain directions. Most of the universe isn't like where we are. Most of it is either denser, packed with galaxy clusters and superclusters, or emptier, deep in the hearts of voids where very few galaxies exist. We happen to be in a transition zone, a cosmic borderland between empty and full. And that location, as random as it might seem, affects everything we see when we look out at the cosmos. It's a profound realization, one that scientists are still grappling with, one that will shape cosmology for years to come. We're inside a cosmic void. We've been here all along, and we only just realized it. Let's go deeper into what astronomers actually see when they map the cosmic void around us. Picture yourself as an astronomer in the early 2000s. You're working with data from the Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken. This survey used a dedicated telescope in New Mexico to photograph large sections of the night sky. But it didn't just take pictures. For millions of galaxies, it measured spectra, the rainbow of light broken down by wavelength. These spectra contain information about each galaxy's composition, temperature, and crucially, its redshift. The redshift tells you how fast the galaxy is moving away from us, which in turn tells you approximately how far away it is. With positions on the sky and distances for millions of galaxies, you can plot their locations in three-dimensional space. And when you do this, when you create these three-dimensional maps, patterns emerge that are invisible in two-dimensional sky surveys. Galaxies aren't randomly scattered. They form structures. Long filaments containing hundreds or thousands of galaxies stretching across hundreds of millions of light-years. Walls. Vast, sheet-like structures where galaxies are concentrated in thin layers. And voids. Enormous regions where galaxies are scarce. The first major void was discovered in 1978 by astronomers Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman. They were surveying galaxies in the constellation Boötes and noticed something strange. There was a large region, about 330 million light-years across, where very few galaxies appeared. At first, they thought it might be an error in their data. Maybe there was dust blocking their view in that direction. Maybe there was some observational bias making galaxies harder to detect in that part of the sky. But careful analysis ruled out these explanations. The void was real. It was an enormous region of space containing far fewer galaxies than expected. They called it the Boötes void, and its discovery changed how astronomers thought about the universe's structure. Before this, voids had been predicted by theoretical models, but finding one this large was surprising. Since then, hundreds of voids have been discovered and mapped. Some are small, just tens of millions of light-years across. Others are enormous, rivaling the KBC Void in size. Each void has its own characteristics. Some are nearly spherical. Others are elongated, stretched along one axis. Some are completely isolated, surrounded by denser regions on all sides. Others connect to neighboring voids, forming chains or networks of underdense regions. The voids themselves aren't completely empty of galaxies. Even in the deepest, emptiest parts of voids, you can still find some galaxies. These are typically small dwarf galaxies or isolated spiral galaxies that somehow ended up far from any major concentration of matter. These void galaxies are interesting in their own right. They exist in an environment completely different from galaxies in clusters or on filaments. They don't interact with neighboring galaxies because there are no neighboring galaxies nearby. They don't experience ram pressure from gas in a dense intergalactic medium Because the void is so empty, there's essentially no intergalactic gas. They evolve in isolation, following their own path. Some astronomers specialize in studying these void galaxies, trying to understand how galaxies behave when they're alone rather than in the crowded environments of clusters. What they've found is that void galaxies tend to be actively forming stars. They have plenty of gas that hasn't been stripped away by interactions with other galaxies or with hot gas in a cluster. They're typically blue in color, indicating young stars. They're smaller and less massive than galaxies in denser regions, probably because there wasn't as much matter available to build them in the first place. But they're survivors. They've existed in these empty regions for billions of years, slowly converting their gas into stars, evolving at their own pace. Now, let's talk about how the void affects the motion of galaxies around us. Gravity is always at work, pulling matter together. In dense regions, this pull is strong. Galaxy clusters are held together by gravity despite the expansion of space. The galaxies within a cluster orbit around their common center of mass, bound by mutual gravitational attraction. In voids, the situation is different. There's very little matter, so the gravitational pull is weak. The expansion of space dominates. Galaxies in voids are moving away from each other faster than galaxies in denser regions, because there's less gravity to slow the expansion. The void itself is expanding. It's getting larger over time as space stretches and the few galaxies inside it move farther apart. This creates what astronomers call a peculiar velocity field. Peculiar velocity is the motion of a galaxy through space, independent of the expansion. It's the galaxy's actual velocity relative to the cosmic reference frame. In a void, galaxies have peculiar velocities directed outward, away from the void's center. The void is essentially pushing matter out toward its edges. Meanwhile, in the dense regions surrounding the void, galaxies have peculiar velocities directed inward, toward concentrations of mass like the centers of superclusters. Gravity is pulling them in. The Milky Way has its own peculiar velocity. We're moving through space at about 373 miles per second relative to the cosmic microwave background, which serves as a universal reference frame. This motion is a combination of several different flows. Part of it comes from our orbit around the center of the Milky Way. Part comes from the Milky Way's motion within the local group. Part comes from the local group's motion toward the Virgo cluster. Part comes from the Virgo cluster's motion toward larger structures like the Great Attractor and the Shapley supercluster. And part of it comes from our position near the edge of the KBC Void. The void is expanding behind us, in a sense, pushing us slightly toward the denser regions ahead. This complex motion reflects the fact that we're embedded in a hierarchy of structures. The void is just one piece of this hierarchy. Measuring these motions and understanding how they relate to the distribution of matter is one of the key goals of modern cosmology. If we can map out the peculiar velocity field accurately, we can work backward to infer the distribution of matter, including dark matter, throughout our cosmic neighborhood. This is challenging because peculiar velocities are small compared to the expansion velocities of distant galaxies. For a galaxy a billion light-years away, the expansion velocity might be 43,000 miles per second. The peculiar velocity might be only a few hundred miles per second. Detecting that small difference requires extremely precise measurements. But astronomers are doing it. Surveys, like the Cosmic Flows Project, have measured peculiar velocities for tens of thousands of galaxies. These measurements reveal the patterns of flow, the streams of galaxies moving toward and away from different structures. And these patterns confirm what we see in the galaxy distribution surveys. There are voids and filaments and clusters, and matter is flowing according to the gravitational fields created by this structure. Now, let's return to the Hubble tension and explore it in more detail. The Hubble constant is one of the most important numbers in cosmology. It tells us how fast the universe is expanding. It determines the age of the universe, how long ago the Big Bang occurred. It affects calculations of distances to remote galaxies. It's fundamental to almost every cosmological measurement. For decades, measuring the Hubble constant was one of the great challenges in astronomy. The difficulty is that you need two things: accurate distances to galaxies and accurate measurements of their velocities. Velocities are easy. You measure redshift, which is straightforward using spectroscopy. But distances are hard. There's no cosmic ruler you can extend across millions of light years. You have to use indirect methods, each with its own uncertainties and potential sources of error. The breakthrough came with the discovery that certain types of objects have predictable intrinsic brightness. These are called standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate its distance using the inverse square law. Light spreads out as it travels, so an object twice as far away appears 4 times dimmer. One of the best standard candles is a Type Ia supernova. These are exploding white dwarf stars. A white dwarf is the remnant of a sun-like star that's exhausted its fuel. It's incredibly dense, packing about the sun's mass into an object the size of Earth. If a white dwarf is part of a binary system with a companion star, it can pull matter from its companion. This matter piles up on the white dwarf's surface, gradually increasing its mass. When the white dwarf reaches a critical mass, about 1.4 times the mass of the Sun, something catastrophic happens. The pressure and temperature at its core become so extreme that carbon fusion ignites throughout the entire star almost simultaneously. The white dwarf explodes. The explosion is so energetic that for a few weeks, the supernova can outshine its entire host galaxy. And here's the key point. Because all Type Ia supernovae involve white dwarfs reaching the same critical mass and undergoing the same type of explosion, they all reach approximately the same peak brightness. They're standardizable candles. There are some variations, but astronomers have learned to correct for these variations using the shape and color of the supernova's light curve. After corrections, Type Ia supernovae are one of the most reliable distance indicators we have. Teams of astronomers have been observing Type Ia supernovae for decades, measuring their distances and redshifts. This work led to the discovery in the late 1990s that the universe's expansion is accelerating, driven by something called dark energy. That discovery won the Nobel Prize in Physics in 2011, but it also provided precise measurements of the Hubble constant. The most recent measurements using Type Ia supernovae, along with other methods like Cepheid variable stars, give a value of about 45.4 miles per second per megaparsec. The uncertainty in this measurement is only about 1%. That's remarkably precise for astronomy. But there's a problem. When cosmologists calculate what the Hubble constant should be based on observations of the early universe, they get a different number. The cosmic microwave background is radiation left over from about 380,000 years after the Big Bang. It fills the entire universe, a faint glow in every direction, with a temperature of about 2.7 Kelvin. This radiation carries information about the conditions in the early universe. By analyzing tiny fluctuations in its temperature across the sky, cosmologists can determine fundamental properties of the universe, including the amount of ordinary matter, and dark energy, and the rate at which the universe is expanding. The Planck satellite, which operated from 2009 to 2013, made the most detailed measurements of the cosmic microwave background ever achieved. Using this data, cosmologists calculated that the Hubble constant should be about 41.9 miles per second per megaparsec. The uncertainty here is also about 1%. Both measurements are precise. Both have been checked and rechecked by independent teams using different data and methods, but they don't agree. The difference is about 2 miles per second per megaparsec, or about 9%. In most fields, a 9% discrepancy wouldn't be cause for alarm. But in cosmology, where measurements are becoming increasingly precise, this discrepancy is significant. It's well beyond the stated uncertainties of both measurements. Something is wrong. Either there's a systematic error in one or both measurements that hasn't been identified, or our understanding of the universe's physics is incomplete. This is the Hubble tension. It's one of the most discussed topics in cosmology right now. Conferences are held about it. Papers are published proposing solutions. Theorists are exploring modifications to the standard cosmological model. Observational astronomers are conducting new measurements to try to resolve it. The KBC Void offers one possible explanation. If we're in a region where the expansion rate is faster than average, our local measurements would give a higher value for the Hubble constant than the true universal average. The cosmic microwave background measurement represents the average expansion rate across the entire observable universe. It's not affected by local structures like voids. But measurements using Type Ia supernovae and Cepheid variables sample our local universe out to a few 100 million light-years. If this local region is systematically different from the cosmic average due to the void, the measurements would be biased. Several research groups have modeled this scenario. They've calculated how large a void would need to be and how underdense it would need to be to explain the full discrepancy. The results are mixed. Some studies suggest a void, like the KBC Void, could explain 1 to 2 miles per second per megaparsec of the discrepancy, roughly half of the observed tension. Other studies are more conservative, suggesting the void can only account for about 1 mile per second per megaparsec. Part of the difficulty is that we don't know the void's properties with perfect precision. The exact size, the exact density contrast, the exact location of our position within it, all of these have uncertainties. Small changes in these parameters affect how much the void biases our measurements. There's also debate about whether the void alone is sufficient or whether other factors are needed. Some astronomers argue that even with the void, there's still unexplained tension. The void helps, but it doesn't solve the entire problem. Others argue that if we properly account for all local structures, not just the void, but also the flows toward the Virgo cluster and Laniakea, the tension might disappear entirely. The debate continues. New data from ongoing surveys will help constrain the void's properties more precisely. The DESI survey, in particular, is mapping millions of galaxies in 3 dimensions, providing unprecedented detail about the large-scale structure around us. As this data is analyzed over the next few years, we'll get a clearer picture of the void and our position within it. We'll be able to calculate its effect on our measurements with greater accuracy. And we'll know whether it can truly explain the Hubble tension or whether we need to look elsewhere for the solution. But regardless of whether the void fully explains the Hubble tension, its existence has important implications. It reminds us that we can't assume our local measurements are representative of the universe as a whole. We need to account for local structures and biases. This is especially important as cosmology enters an era of precision measurements. When uncertainties are small, even subtle effects become significant. A void that changes the expansion rate by just a few percent can throw off measurements and lead to incorrect conclusions about the universe's properties. Accounting for these effects requires detailed knowledge of our cosmic neighborhood. We need maps of galaxy distributions. We need measurements of peculiar velocities. We need models of how matter is distributed in 3 dimensions, including dark matter that we can't see directly. All of this is work that astronomers are actively pursuing. The goal is to build a complete 3-dimensional model of the local universe out to a few billion light-years. This model would include all known structures, clusters, filaments, voids, and would allow us to correct our measurements for local biases. With such a model, we could determine whether our measurements of the Hubble constant are truly representative of the universe or are skewed by our location. We could predict what an observer in a different location, say in the center of a dense supercluster, would measure. And we could reconcile different measurements, understanding how much of the variation is due to cosmic variance and local structure rather than fundamental physics. This is the future of cosmology, not just taking measurements, but understanding the context of those measurements, understanding where we are, what's around us, and how that affects what we see. Let's talk about what other discoveries might be hidden in plain sight, waiting for us to notice them. The KBC Void was discovered only recently, despite being right on our cosmic doorstep. What else might we have missed? One possibility is that the void is even larger than we think. Current measurements suggest it's about 2 billion light-years across. But those measurements rely on galaxy surveys that may not extend far enough to capture the void's full extent. If the void extends farther, its effects on our observations would be correspondingly stronger. We might need to revise our estimates of how much it affects the Hubble constant measurement. We might also find that other measurements, things we thought we understood, are actually being influenced by the void in ways we haven't accounted for. Another possibility is that there are other voids nearby that we haven't fully characterized. The universe's structure is complex. Voids can be adjacent to each other, separated only by thin filaments of galaxies. We might be near the edge, not just of one void, but of a complex system of interconnected voids. If that's the case, the total effect on our observations could be larger than what we'd calculate from the KBC Void alone. There's also the question of what's happening at the center of the void. We're on the edge, about 700 million light-years from the center. The center itself is extremely underdense, with very few galaxies. What would an observer there see? If there were a civilization at the center of the KBC Void, their night sky would be dramatically different from ours. They'd see far fewer galaxies. The nearest significant galaxy clusters would be about 1 billion light-years away, appearing as faint, distant smudges even through powerful telescopes. Their measurements of the universe would be even more affected by their location than ours are. They'd measure an even higher expansion rate, an even stronger Hubble tension. They might conclude that the universe is expanding much faster than it actually is on average. They'd be more isolated in a cosmic sense, farther from other concentrations of matter and life. Of course, this assumes such a civilization could even arise. Galaxies at the center of voids tend to be small and gas-rich, still actively forming stars. They're not the old, stable galaxies where you'd expect advanced civilizations to develop. But it's an interesting thought experiment. How different would cosmology look if we were even deeper in a void? How much harder would it be to understand the universe's true structure? On the flip side, what if we were in a dense region, at the center of a galaxy cluster? We'd see many more galaxies in our night sky. Interactions and mergers would be common. Our measurements of the expansion rate would be lower than average because gravity would be slowing the expansion in our region. We'd have a different set of biases to account for, a different perspective on the cosmos. The point is, every location has its own biases. There's no perfectly neutral vantage point from which to observe the universe. Wherever you are, your measurements are affected by your environment. The key is recognizing these biases and correcting for them. That's what astronomers are doing now with the KBC Void. They're not just discovering that we're in a void. They're quantifying the void's properties, modeling its effects, and using that understanding to correct our measurements. This is science at its best. Recognizing limitations, characterizing them, and overcoming them through careful analysis. Let me bring this back to something more immediate and tangible. What does it mean for us, as individuals, to learn that we're in a void? On a practical level, it doesn't change anything about our daily lives. The void is so large and its effects so subtle that you'd never notice it without precise astronomical instruments. You still see the same stars in the night sky. The sun still rises and sets. Your life goes on unchanged. But on a deeper level, this discovery is part of humanity's ongoing journey to understand our place in the cosmos. For most of human history, we thought we were special, at the center of creation, the focus of the universe's attention. Science has repeatedly shown us that we're not special in that way. We're not at the center. We're not the focus. We're just one planet among billions, orbiting one star among hundreds of billions, in one galaxy among trillions. Each discovery pushed us further from any notion of cosmic significance. Being in a void is the latest step in this journey. Not only are we not at the center, we're in one of the emptier regions of space, a place where galaxies are scarce, a cosmic backwater, in a sense. Some people find this depressing. If we're so insignificant, if our location is so unremarkable or even less than remarkable, what does that say about the meaning of our existence? But there's another way to look at it. Yes, we're small. Yes, we're in a void. But we're also here, conscious and aware, capable of asking questions about our place in the universe. We've measured the void. We've understood its properties. We've figured out how it affects our observations. From this remote location, on the edge of emptiness, we've reached out with our minds and our instruments and mapped the cosmos. That's extraordinary. The fact that conscious beings can arise anywhere in the universe, even in voids, even in regions where matter is scarce and galaxies are few, speaks to the resilience and adaptability of life. We don't need to be at the center of everything to matter. We don't need to be in the densest region of space to have significance. We create our own significance through our actions, our curiosity, our drive to understand. The universe doesn't care where we are. It doesn't care whether we're in a void or a cluster. But we care. We ask questions. We seek answers. And in doing so, we give meaning to our existence. That's the human story. Not that we're cosmically significant in some objective sense, but that we're able to recognize our insignificance and find meaning despite it, or perhaps because of it. The vastness of the universe, the emptiness of the void, these things make our existence more remarkable, not less. Against all odds, in this tiny corner of a vast cosmos, matter organized itself into stars and planets, and eventually into living things, capable of understanding their own cosmic context. That's amazing. And it remains amazing whether we're in a void or anywhere else. So yes, we're in a cosmic void. We've been here all along, and we only just realized it. But that realization doesn't diminish us. If anything, it showcases our ability to overcome our limitations and see past our local environment to understand the universe as it truly is. That's what makes us human. Not our physical location, not our cosmic significance, but our curiosity and our determination to understand. We're in a void, but we're also extraordinary. And those two facts can coexist without contradiction. Thanks for staying with me through this journey across the largest scales of space. The void we inhabit stretches nearly 2 billion light-years across, but the questions it raises reach even further. What other biases are hidden in our cosmic perspective? What other surprises await us as we continue mapping the universe? These are the questions that drive cosmology forward, pushing us to look deeper, measure more precisely, and challenge our assumptions about our place in the cosmos. The void is immense, but our capacity to understand it is extraordinary. Let's take a step back and look at the broader context of how this discovery fits into the history of cosmology. Understanding the universe's large-scale structure is a relatively recent achievement. For most of human history, we had no idea that galaxies even existed beyond our own. The Milky Way was thought to be the entire universe. Those fuzzy patches of light visible through telescopes, objects we now know are distant galaxies, were called nebulae and were assumed to be clouds of gas within our galaxy. This view persisted well into the early 20th century. In 1920, there was actually a famous debate between two astronomers, Harlow Shapley and Heber Curtis, about the nature of these spiral nebulae. Shapley argued they were part of the Milky Way. Curtis argued they were separate island universes, galaxies in their own right, far beyond the bounds of our galaxy. The debate couldn't be settled because distance measurements weren't good enough. But in 1923 and 1924, Edwin Hubble changed everything. Using the largest telescope in the world at the time, the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble observed Cepheid variable stars in the Andromeda Nebula. Cepheids are stars that pulsate, brightening and dimming with a regular period. Their period of pulsation is directly related to their intrinsic luminosity. By measuring a Cepheid's period, you can determine how bright it actually is. By comparing that to how bright it appears from Earth, you can calculate its distance. Hubble found Cepheids in Andromeda and measured their distances. The results were stunning. Andromeda was about 900,000 light-years away, far beyond any distance within the Milky Way. It wasn't a nebula within our galaxy. It was a separate galaxy, comparable in size to the Milky Way. This discovery revolutionized astronomy overnight. If Andromeda was a separate galaxy, then other spiral nebulae probably were too. The universe was suddenly far larger than anyone had imagined. Instead of one galaxy, there were countless galaxies scattered throughout space. Hubble continued his work, measuring distances to more and more galaxies. In 1929, he published another groundbreaking discovery. The farther away a galaxy was, the faster it was moving away from us. This relationship between distance and velocity became known as Hubble's law, and it implied something profound. The universe was expanding. Space itself was growing, carrying galaxies along with it. This led to the development of the Big Bang theory, the idea that the universe started from an extremely hot, dense state and has been expanding and cooling ever since. But understanding the distribution of galaxies in 3 dimensions took much longer. Measuring distances is hard. You need standard candles or other distance indicators, and these are only available for relatively nearby objects. For most galaxies, all you can easily measure is their redshift, which tells you their velocity, but not directly their distance. The breakthrough came with the realization that for distant enough galaxies, the velocity is dominated by the expansion of space rather than peculiar motion. This means redshift can be used as a proxy for distance. A galaxy with twice the redshift is approximately twice as far away. This allowed astronomers to start mapping the 3-dimensional distribution of galaxies. By the 1970s and 80s, surveys were beginning to reveal structure. Galaxies weren't randomly distributed. They formed clusters and groups, and there were hints of larger structures, filaments and walls. The CFA Redshift Survey, conducted at the Harvard-Smithsonian Center for Astrophysics in the 1980s, was one of the first to reveal these structures clearly. When they plotted galaxy positions in 3 dimensions, a pattern emerged. Galaxies were arranged in sheets and filaments surrounding voids. One structure, discovered in this survey, became famous. The CFA 2 Great Wall, a vast sheet of galaxies stretching about 500 million light-years across. It was one of the largest structures known at the time, and it showed that the universe had structure on scales far larger than individual galaxy clusters. The 1980s and 90s saw rapid progress. Better telescopes, better detectors, and better computers allowed astronomers to survey larger volumes of space with greater precision. The Las Campanas Redshift Survey, the 2-degree field galaxy redshift survey, and eventually the Sloan Digital Sky Survey mapped millions of galaxies. Each survey revealed more of the cosmic web. More filaments, more walls, more voids. The picture that emerged is the one we have today. A universe filled with structure at all scales, from individual galaxies to superclusters spanning hundreds of millions of light-years, all arranged in a web-like pattern surrounding enormous voids. The KBC Void is part of this structure. It's a particularly large void in our local neighborhood, but it's not fundamentally different from other voids throughout the universe. What makes it significant is that we're in it, or rather, on its edge. This affects our measurements and our perspective, and recognizing this fact has taken decades of careful mapping and analysis. It's only in the past decade or so, as surveys have become comprehensive enough to map the structure around us in detail, that the void's existence and our position within it have become clear. This is how science progresses. Slowly, through accumulation of data and refinement of understanding, early hints become clearer as more data comes in. Patterns that seemed ambiguous become obvious in retrospect. And occasionally, a new discovery forces us to reconsider everything we thought we knew. The void isn't quite that revolutionary. It doesn't overturn our basic models of cosmology, but it does add an important detail. It tells us that when we make measurements from Earth, we need to account for our local environment. We're not observing from a neutral vantage point. We're observing from within a particular structure that has particular properties, and those properties affect what we see. Now, let's talk about dark matter and dark energy in the context of the void. These two mysterious substances make up most of the universe's content. Ordinary matter, the stuff we're made of, the atoms and molecules that make up stars and planets and gas, accounts for only about 5% of the universe's total mass energy. Dark matter makes up about 27%. Dark energy makes up the remaining 68%. Dark matter is called dark because it doesn't interact with light. It doesn't emit, absorb, or reflect electromagnetic radiation. We can't see it directly, but we know it exists because of its gravitational effect. Galaxies rotate faster than they should based on their visible matter alone. Galaxy clusters contain more mass than can be accounted for by their stars and gas. Gravitational lensing, the bending of light by gravity, shows the presence of large amounts of invisible matter in and around galaxy clusters. All of these observations point to the existence of dark matter. We don't know what it's made of. The leading candidates are exotic particles that haven't been detected in laboratories yet. Experiments are ongoing to try to detect these particles directly, but so far, they've remained elusive. Despite not knowing its composition, we know a lot about dark matter's properties and distribution. It clusters under gravity, just like ordinary matter, but it doesn't collide or interact with itself or ordinary matter, except through gravity. This means it can pass through clouds of gas without slowing down, and it can form halos around galaxies without getting tangled up in the stars and gas. Dark matter is what provides the gravitational scaffolding for structure formation. In the early universe, dark matter clumped together first, forming halos. Ordinary matter then fell into these halos, where it could cool and condense to form galaxies. Without dark matter, galaxies as we know them couldn't exist. There wouldn't be enough gravity to hold them together. In voids, there's less dark matter than in denser regions, but it's not completely absent. The void still has a weak gravitational field due to the dark matter that's present, and this field affects how galaxies move and how light travels through the void. The distribution of dark matter in and around voids is something astronomers study using gravitational lensing and the motion of galaxies. By tracking how galaxies move, you can infer the gravitational field, which in turn tells you where the dark matter is. These studies show that voids have dark matter distributed throughout them, just at lower density than in filaments and clusters. The underdensity is similar for dark matter and ordinary matter. Voids are about 20 to 30% underdense in both. Now let's talk about dark energy. Dark energy is even more mysterious than dark matter. It's a property of space itself, a sort of intrinsic energy that causes the universe's expansion to accelerate. The existence of dark energy was discovered in 1998 through observations of distant Type Ia supernovae. Astronomers expected that the universe's expansion should be slowing down over time due to gravity, but instead, they found that the expansion is speeding up. Distant supernovae were dimmer than expected, indicating they were farther away than they should be if the expansion was slowing. This could only be explained if something was pushing space apart, counteracting gravity. That something is dark energy. We don't know what dark energy is or why it exists. The simplest explanation is that it's the vacuum energy of space, a sort of background energy that exists even in empty space. Quantum mechanics predicts that empty space should have energy due to quantum fluctuations. But when you try to calculate how much energy space should have, you get a number that's vastly larger than what observations show, off by about 120 orders of magnitude, which is one of the biggest discrepancies in all of physics. So we know dark energy exists, but we don't understand its nature or origin. What we do know is that it causes the universe's expansion to accelerate. This acceleration affects how structures grow and evolve. In the early universe, before dark energy became dominant, gravity was winning. Dense regions were collapsing, forming galaxies and clusters. Voids were growing, but relatively slowly. But as the universe expanded, and dark matter and ordinary matter became more spread out, dark energy, which has constant density throughout space, became more important. Dark energy doesn't dilute as space expands. Its density remains constant. So as other forms of matter and energy become less dense due to expansion, dark energy's relative importance grows. Today, dark energy is the dominant component of the universe's energy budget. It's causing the expansion to accelerate, and this acceleration affects structure formation. In particular, it affects voids. Voids are regions where dark energy's repulsive effect is relatively stronger because there's less matter to counteract it with gravity. This means voids are expanding faster than they would in a universe without dark energy. They're growing, becoming emptier, as their few remaining galaxies are pushed toward the edges by the accelerating expansion. Over billions of years, this process will continue. Voids will become vast, empty regions with essentially no galaxies inside them. The cosmic web will become more pronounced, with filaments and clusters standing out more starkly against the emptiness of the voids. Eventually, in the far future, trillions of years from now, the acceleration will become so extreme that even bound structures like galaxy clusters will begin to be torn apart. This scenario is sometimes called the Big Rip, though it's not certain if the universe will end this way. It depends on the properties of dark energy, which we're still working to measure. But, regardless of the ultimate fate, dark energy is shaping the universe's structure right now. It's affecting voids, filaments, clusters, everything. And understanding its effects is crucial for interpreting observations of the universe's large-scale structure. The KBC Void is a laboratory for studying both dark matter and dark energy. By measuring the void's properties, its size, its density profile, how it's growing over time, astronomers can constrain the properties of dark matter and dark energy. Different models make different predictions about how voids should behave, and observations can test these predictions. This is one reason why studying the void is important. It's not just about understanding our local environment. It's about testing fundamental physics. Let's talk about what the future holds for studies of the void and cosmic structure in general. As I've mentioned, several major surveys are underway or planned for the next decade. The DESI survey, the Dark Energy Spectroscopic Instrument, is currently mapping the universe in unprecedented detail. It's designed to measure redshifts for tens of millions of galaxies, creating a three-dimensional map that covers a huge volume of space. DESI's goal is to study dark energy by measuring how the universe's expansion has changed over time. But along the way, it's also mapping structure, including voids like the KBC Void. The data from DESI will allow astronomers to characterize the void more precisely than ever before. They'll be able to measure its exact size, its density profile, how it transitions to the surrounding filaments, and how our position within it affects our measurements. This will help determine whether the void can fully explain the Hubble tension or whether other factors are needed. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is another major project. It's a ground-based telescope with an enormous field of view, designed to survey the entire visible sky every few nights. Over 10 years, it will create a detailed movie of the universe, tracking how objects move and change. For structure studies, Rubin Observatory will provide photometric redshifts for billions of galaxies. These are less accurate than spectroscopic redshifts, but the sheer number of galaxies will make up for the lower precision. The resulting map will cover the largest volume of space ever surveyed. Then there's the Nancy Grace Roman Space Telescope, named after NASA's first chief of astronomy. This is a space-based telescope with a field of view 100 times larger than Hubble's. It's designed to study dark energy, but it will also survey the structure of the distant universe. Roman will see galaxies at earlier times, when the universe was younger and the cosmic web was still forming. By comparing these early structures to the present-day structure around us, astronomers can trace how voids and filaments evolved over billions of years. These surveys, along with others like Euclid, a European Space Agency mission, will revolutionize our understanding of large-scale structure. They'll provide datasets, orders of magnitude, larger than anything available today. And they'll allow tests of cosmological models with unprecedented precision. One key question they'll address is whether the standard cosmological model, lambda CDM, can explain everything we observe. Lambda CDM is our current best model. Lambda represents dark energy, and CDM stands for cold dark matter. Lambda CDM has been incredibly successful. It explains the cosmic microwave background, the distribution of galaxies, the expansion history of the universe, and many other observations. But there are hints that it might be incomplete. The Hubble tension is one hint. Another is the so-called sigma-8 tension, a discrepancy in measurements of how clumpy the universe is at different scales. There are also questions about whether the largest structures, like the Hercules Corona Borealis Great Wall, are consistent with lambda CDM predictions. The KBC Void fits into this picture as another potential discrepancy. If the void is larger or more extreme than lambda CDM predicts should be possible, that would be evidence that something in our models needs adjusting. The upcoming surveys will help resolve these questions. They'll provide the data needed to test whether lambda CDM is correct or whether modifications are needed. Maybe dark energy isn't a simple cosmological constant, but something more complex that evolves over time. Maybe dark matter has interactions we haven't accounted for. Maybe there are other forms of energy or matter we haven't discovered. These are exciting possibilities because they point toward new physics beyond the standard model. Every major advance in cosmology has revealed new layers of complexity and opened up new questions. The discovery of the cosmic microwave background confirmed the Big Bang model, but also raised questions about the early universe that led to the theory of inflation. The discovery of dark matter solved some problems, but created new mysteries about what particles make it up. The discovery of dark energy explained the accelerating expansion, but raised deep questions about the vacuum energy of space. The KBC Void might be the next piece of this puzzle. It might be a clue that leads us to deeper understanding of how the universe works. Or it might simply be an interesting feature of our local neighborhood that we need to account for in our measurements. Either way, studying it is important. It's part of the ongoing effort to build a complete, accurate picture of the cosmos. Before we close, let's explore what observing the universe from different locations would actually look like. This thought experiment will help us appreciate how much our location in the KBC Void affects our cosmic perspective. Imagine you're an astronomer on a planet, in a galaxy at the center of the void. About 1 billion light-years from the nearest significant cluster of galaxies in any direction. Your night sky would be profoundly different from ours. First, there would be far fewer visible galaxies. Even with powerful telescopes, you'd struggle to find nearby galaxies. The handful of small dwarf galaxies scattered through the void would be the only neighbors within hundreds of millions of light years. Your galaxy surveys would show enormous empty volumes in all directions. The nearest galaxy clusters would be distant smudges, barely visible even through your largest instruments. When you measured the expansion rate of the universe, you'd get a very high value, much higher than the true cosmic average, because in the deep void, space expands faster than elsewhere. There's almost no matter to slow the expansion. Dark energy dominates completely. If you calculated the age of the universe based on this high expansion rate, you'd get a younger age than the true age. You might conclude the universe is only 10 or 11 billion years old when it's actually 13.8 billion. Your measurements of the universe's matter density would also be off. You'd measure much less matter than actually exists on average, because your local region is severely underdense. You might conclude that ordinary and dark matter make up only a few percent of the universe when they actually make up 32% combined. Your entire cosmology would be skewed by your location. Now, imagine the opposite scenario. You're on a planet, in a galaxy, at the center of a massive galaxy cluster, the Coma cluster, for instance, which contains over 1,000 galaxies. Your night sky would be crowded. Hundreds of galaxies would be visible to the naked eye as fuzzy patches of light. Your nearest galactic neighbors would be only a few million light years away, close enough to show detailed structure through telescopes. Galaxy interactions and mergers would be common. Your own galaxy might be tidally disrupted by close passes with neighbors. When you measured the expansion rate, you'd get a lower value than the cosmic average. The cluster is gravitationally bound, so there's no expansion within it. And even outside the cluster, the dense surrounding region would expand more slowly than voids. If you only measured nearby objects, you might conclude the expansion rate is much lower than it actually is, on average. You might calculate an older age for the universe, perhaps 15 or 16 billion years, because you'd think the expansion has been proceeding more slowly. Your measurements of matter density would be much higher than average, because you're in an overdense region. You might conclude the universe is much more matter-dominated than it actually is. These two extreme examples show how location matters. Neither observer is wrong in what they measure locally. The expansion rate really is higher in voids and lower in dense regions. But both would be wrong if they assumed their local measurements represented the universe as a whole. Only by recognizing that they're in unusual locations and correcting for this bias could they arrive at accurate, universal values. This is exactly the situation we're in with the KBC Void. We're not at the extreme center of the void, so our measurements aren't as skewed as they would be there. But we're on the edge, and that's enough to introduce measurable bias. The question is how much bias? Can we quantify it precisely enough to correct our measurements? That's what current research is trying to determine. Different studies have different conclusions, which tells us there's still uncertainty in our understanding of the void's properties and effects. Let's also consider how this discovery affects our search for life in the universe. The question of whether we're alone in the cosmos is one of humanity's oldest and most profound questions. For decades, astronomers have been searching for signs of life beyond Earth. We've sent probes to Mars and other planets in our solar system. We've discovered thousands of exoplanets orbiting other stars. We've listened for radio signals that might indicate technological civilizations. So far, we've found nothing. No definitive evidence of life beyond Earth. This lack of evidence has led to various theories about why we haven't found anyone. Maybe life is extremely rare, requiring such specific conditions that Earth might be one of only a handful of living worlds in the entire observable universe. Maybe life is common, but intelligence is rare, with most living worlds hosting only simple microbes. Maybe technological civilizations destroy themselves before they can communicate across interstellar distances. Maybe advanced civilizations deliberately hide themselves or have no interest in contacting us. These ideas form what's called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Being in the KBC Void adds an interesting dimension to this question. If we're in an underdense region of the universe, does that affect the likelihood of nearby civilizations? On one hand, probably not significantly. Galaxies in voids still form stars. Those stars still have planets, and those planets can still develop life if conditions are right. The void doesn't change the fundamental chemistry and physics that allow life to emerge. But on the other hand, galaxies in voids tend to be smaller and less massive than galaxies in dense regions. They have fewer stars, which means fewer planets, which means fewer opportunities for life to arise. The void also means greater isolation. Even if civilizations exist in void galaxies, they're farther apart than civilizations in dense regions would be. The nearest alien civilization might be in another galaxy hundreds of millions of light years away, rather than in a nearby galaxy just a few million light years away. Communication across such distances would be essentially impossible. Even at the speed of light, messages would take hundreds of millions of years to travel. By the time a reply arrived, the civilization that sent the original message would likely be long extinct. So being in a void might make us more isolated than we would be in a denser region of the universe. It doesn't mean we're alone in the universe. The universe is vast, containing trillions of galaxies. Even if voids are less densely populated with life than other regions, there should still be countless living worlds scattered throughout the cosmos. But it might mean that the nearest neighbors are farther away than they would be if we were in a more typical location. This has implications for the search for extraterrestrial intelligence. If we're in a region where civilizations are more spread out, we might need to search farther and wait longer for any signal. The probability of detecting a nearby civilization drops if nearby means hundreds of millions of light years rather than just a few million. Of course, this is all speculation. We don't know how common life is or where it arises. We don't know if intelligence is a common outcome of evolution or a rare fluke. We don't know if technological civilizations last long enough to communicate across cosmic distances. But location matters. Being in a void affects the density of galaxies around us, which affects the density of stars, which affects the density of planets, which affects the density of potential living worlds. It's one more factor to consider in the already complex question of life in the universe. Let me conclude by circling back to where we started. Tonight, we set out to understand what it means that we're living inside a cosmic void. We've covered a lot of ground. We started with the basic concept of voids as underdense regions in the cosmic web. We learned how voids form through gravitational instability, as matter clusters in some regions and evacuates from others over billions of years. We discovered that the KBC Void is one of the largest voids in the local universe, stretching about 2 billion light-years across. We learned that our Milky Way galaxy sits not at the center, but on the edge of this void, about 700 million light-years from its center. We explored how being in this void affects our astronomical measurements, particularly the Hubble constant, which measures the expansion rate of the universe. We discussed the Hubble tension, the discrepancy between different measurements of this constant, and how the void might explain part or all of this discrepancy. We looked at the history of how this void was discovered through painstaking galaxy surveys that mapped the three-dimensional structure of the universe around us. We considered the philosophical implications of learning that we're not in a typical location, that our vantage point has biases that affect what we observe. We discussed dark matter and dark energy, the mysterious substances that make up most of the universe, and how they relate to void properties and evolution. And we looked ahead to future surveys and observations that will refine our understanding of the void and test whether our cosmological models are correct. Throughout this journey, one theme has emerged. Our understanding of the universe is shaped by our perspective. We observe from one location at one time, and that location has properties that affect our observations. For centuries, we assumed we were in a special location, at the center of everything. Then we learned we weren't special at all, just another random spot in the cosmos. Now we're learning that while we're not special in the sense of being central or unique, our location does have specific characteristics that affect our measurements. We're in a void, or more precisely, on the edge of one. And recognizing this fact is crucial for correctly interpreting our observations and understanding the universe as it truly is, not just as it appears from our biased vantage point. This is the nature of science. It's an ongoing process of refinement. We make observations, form theories, test those theories, and revise them when observations don't match predictions. We discover biases in our measurements and work to correct for them. We find surprising features like the KBC Void and figure out how they fit into the larger picture. Each generation of astronomers pushes our understanding a little further. Edwin Hubble showed us the universe is full of galaxies and is expanding. Vera Rubin and others discovered dark matter. Saul Perlmutter, Brian Schmidt, and Adam Riess discovered dark energy. And now, today's astronomers are mapping the cosmic web, discovering voids and filaments, and working out how our local environment affects our cosmic perspective. This work will continue. The surveys launching in the next few years will provide data that will keep astronomers busy for decades. New discoveries will emerge from this data. New puzzles will be revealed. And slowly, piece by piece, our picture of the universe will become more complete. The void we live in is just one piece of this picture, but it's an important piece. One that reminds us of both our limitations and our capabilities. Our limitation is that we're confined to one viewpoint, one location in the vast cosmos. We can't step outside and view the universe objectively from nowhere. We're always observing from somewhere, and that somewhere has properties that affect what we see. But our capability is extraordinary. Despite being confined to this one planet, orbiting this one star, in this one galaxy, on the edge of this one void, we've managed to map the universe. We've measured its age, traced its history, predicted its future. We've discovered its composition, mostly dark matter and dark energy that we can't directly see. We've found that it's expanding and accelerating. We've mapped its structure, the cosmic web of filaments and voids stretching across billions of light years. And we've figured out that we're in a void, that we've been in a void all along, that this void affects our measurements, and that we need to account for it to correctly understand the universe. That's an incredible achievement. It demonstrates the power of observation, measurement, mathematics, and reason. It shows what humans can accomplish when we ask questions about the universe and pursue answers with determination and rigor. So, yes, we're in a void, an enormous empty region of space, a place where galaxies are scarce and the expansion of space proceeds faster than average. A location that's statistically unusual in terms of galaxy density, though perhaps not unusual in terms of volume, since voids make up most of space. But being in this void doesn't diminish us. If anything, it makes our achievements more remarkable. From this remote location, on the edge of emptiness, we've reached out across the cosmos with our telescopes and our minds. We've measured distances that dwarf our planet, our solar system, our entire galaxy. We've looked back, in time, to the early universe. We've detected ripples in the fabric of space-time itself. We've photographed black holes. We've found planets around other stars. We've mapped the cosmic web. And we're continuing to push further, to ask deeper questions, to probe the nature of reality at its most fundamental level. The void is vast, but so is our curiosity. The universe is incomprehensibly large, but so is our drive to comprehend it. We may be small, we may be in an underdense region of space, but we are here, and we are aware, and we are asking questions, and that makes all the difference. Thanks for staying with me through this exploration of one of cosmology's most fascinating recent discoveries. I hope you've gained not just an understanding of what the KBC Void is, but also an appreciation for how much we still have to learn about our universe. The void was hiding in plain sight all along, surrounding us, affecting our observations. And we only just noticed it in the past few years, as our maps of the cosmic structure became detailed enough to reveal it. What else is hiding in plain sight? What other features of the universe are we missing because we haven't looked carefully enough or haven't collected enough data? These are the questions that drive cosmology forward. The answers will come from the ongoing surveys, from new telescopes and observatories, from careful analysis of data, and from brilliant theorists proposing new ideas to explain what we observe. The next decade will be an exciting time in cosmology. We'll learn more about the void, about the Hubble tension, about dark matter and dark energy, about the universe's structure and history. We'll answer some questions and discover new ones. And through it all, we'll be working from our particular vantage point on the edge of a cosmic void, doing our best to see past our local biases and understand the universe as it truly is. That's the journey of science. A journey of discovery that never ends, because there's always more to learn, always deeper layers of reality to uncover. The void we discovered is just the latest chapter in this journey, and there are many more chapters yet to be written. Let's spend some time thinking about what cosmic variance means for our understanding of the universe. Cosmic variance is the idea that different regions of the universe will show different properties simply due to statistical fluctuations. Imagine you're trying to determine the average density of matter in the universe. You can't measure the entire universe, so you sample a region of space. But your sample might happen to include more voids or more clusters than average. This introduces uncertainty in your measurement. The smaller your sample, the larger the cosmic variance. If you sample only a small region, your measurement might be significantly different from the true universal average. If you sample a larger region, the variations average out and your measurement becomes more accurate. The KBC Void is an example of cosmic variance at work. Our local region happens to be underdense compared to the universal average. If we only measured properties of our local universe out to a few 100 million light-years, we'd get biased results. To overcome cosmic variance, we need to sample large volumes of space. This is one reason why modern surveys aim to map billions of galaxies spread across huge distances. By sampling large volumes, they reduce the effects of cosmic variance and get measurements that more accurately reflect universal properties. But there's always some residual cosmic variance. Even the largest surveys sample only a fraction of the observable universe. There could be variations on scales larger than what we've mapped. Maybe our entire observable universe happens to be slightly denser or less dense than the true average across all of space. We'd have no way to know because we can't observe beyond the observable universe. This is a fundamental limitation. We can reduce cosmic variance by observing larger and larger volumes, but we can never eliminate it completely. There's always the possibility that we're in an unusual region at some scale. The void is a concrete example of this. At scales of a few 100 million light-years, we're in a typical region. But at scales of a few billion light-years, we're on the edge of an unusually large, underdense region. If we didn't know about the void, we might misinterpret measurements affected by it. Now that we know about it, we can try to correct for it. But there might be other variations at even larger scales that we don't yet know about. Variations that are affecting our measurements in ways we haven't recognized. This is the challenge of observational cosmology. We're trying to measure universal properties from a single vantage point within the universe. We're doing our best to account for local variations, but we can never be completely certain we've accounted for everything. The best we can do is measure as large a volume as possible, look for patterns and variations, model their effects, and make corrections as needed, and be humble about the uncertainties that remain. Let me talk about one more fascinating aspect of voids, their role in the overall evolution of the universe. Voids aren't static. They're growing over time as the universe expands. In the early universe, shortly after the Big Bang, the contrast between dense and empty regions was much smaller than it is today. Matter was distributed much more uniformly. The fluctuations that would eventually become voids and filaments were tiny, barely detectable differences in density. Over billions of years, gravity amplified these differences. Dense regions attracted matter and became denser. Underdense regions lost matter and became emptier. This process continues today. Voids are still growing, still becoming emptier as their remaining galaxies drift toward the edges. Eventually, in the far future, voids will be enormous and completely empty. The few galaxies that exist inside them today will have either drifted out to the edges or become so isolated that they're essentially alone in vast bubbles of empty space. Meanwhile, the filaments and clusters will continue to evolve as well. Galaxies within filaments will gradually fall toward the nearest cluster drawn by gravity. Clusters will merge with neighboring clusters, forming ever larger structures. The cosmic web will become more pronounced, with denser nodes connected by thinner filaments, all surrounded by enormous empty voids. But this process won't continue forever. Dark energy is causing the expansion of the universe to accelerate. As time goes on, the acceleration will become stronger. Eventually, in tens of billions of years, it will become so strong that it will overcome gravity, even in bound structures like galaxy clusters. Clusters will begin to stretch apart. Galaxies will be torn from their clusters and become isolated. Even individual galaxies might eventually be torn apart as the expansion accelerates to extreme levels. This is one possible fate of the universe, sometimes called the Big Rip. Whether it actually happens depends on the properties of dark energy, which we're still working to measure precisely. If dark energy remains constant, as current observations suggest, the universe won't end in a big rip. Instead, it will expand forever, becoming increasingly cold and empty. Stars will burn out. Galaxies will fade. Eventually, only black holes will remain, and even those will eventually evaporate through Hawking radiation. The universe will approach a state of maximum entropy, a cold, dark, empty space where nothing happens anymore. This is called heat death, and it's the most likely fate based on our current understanding. But regardless of which scenario plays out, voids will play an important role in the universe's evolution. They're the regions where dark energy's effects are strongest because there's less matter to counteract it. They're laboratories for studying how the universe will evolve in the far future when dark energy completely dominates. By understanding voids, we gain insight into the universe's ultimate fate. Let me bring this full circle one last time with a reflection on what this means for humanity. We are a species that asks questions. We look up at the night sky and wonder what's out there. We build telescopes to see farther. We develop mathematics to understand what we see. We create theories to explain the patterns. And we test those theories against observation. This process has revealed a universe far stranger and more magnificent than our ancestors could have imagined. We've learned that Earth is not the center, but a small planet orbiting an ordinary star. We've learned that our star is one among hundreds of billions in a galaxy that's one among trillions. We've learned that the universe began in a hot, dense state and has been expanding ever since. We've learned that most of the universe is made of mysterious, dark matter and dark energy that we can't directly see. And now we've learned that we're in a void. An enormous, empty region that's affecting how we see the rest of the cosmos. Each discovery has been humbling. Each one has shown us that we're smaller and less central than we thought. But each discovery has also been empowering. It's shown that despite our smallness, despite our limitations, we can understand the universe. We can measure it. We can map it. We can predict how it will evolve. The void is just the latest example of this. Yes, it shows that our location has biases we need to account for. Yes, it shows that we're in an underdense region, not a typical spot. But it also shows that we can recognize these biases. We can measure the void. We can calculate its effects. We can correct our observations. From our small planet on the edge of a cosmic void, we're reaching out to understand the entire universe. And we're succeeding. That's the human story. Not that we're cosmically important, but that we're cosmically curious. Not that the universe cares about us, but that we care about the universe. Not that we occupy a special place, but that we can understand our place, despite its ordinariness. We're in a void, yes. But we're also remarkable. We're conscious matter that has organized itself to the point where it can contemplate its own origins and its own cosmic context. We're atoms that have learned to wonder about atoms. We're dust that has learned to study dust. We're void dwellers who have learned to map the void. And that's extraordinary. So, when you look up at the night sky tonight, remember what you've learned. You're seeing the universe from a particular vantage point. The edge of a void, 2 billion light-years across. A region where matter is scarce and space expands faster than average. A location that biases your observations in subtle ways. but you're also seeing the universe with the accumulated knowledge of generations of astronomers who worked to understand that vantage point, who measured the void, who mapped its properties, who calculated its effects on our observations, who gave us the tools to see past our local environment and understand the cosmos as it truly is. You're in a void, but you're not alone in your ignorance. You're part of a species that has overcome that ignorance through centuries of careful observation and thought. You're part of a tradition that started with ancient astronomers who wondered about those points of light in the sky. That continued with Galileo pointing his telescope at Jupiter and seeing moons, with Hubble discovering that the universe is vast and expanding, with Rubin discovering dark matter, with Perlmutter, Schmidt, and Rius discovering dark energy, and with modern astronomers discovering the void. Each generation built on the work of those before. Each pushed our understanding a little further. And the work continues. The void we've discovered is not the end of the story. It's a chapter in an ongoing narrative of discovery. Future astronomers will refine our measurements. They'll discover new structures. They'll answer questions we haven't thought to ask yet, and they'll pass their knowledge to the next generation, who will continue the work. This is the legacy we inherit and pass on. The knowledge that we're small but capable, limited but determined, in a void but not empty. We're cosmic explorers, reaching out from our tiny world to comprehend the vastness around us. And that makes us, in our own small way, magnificent. The void is immense. 2 billion light-years of near emptiness stretching in certain directions from our galactic home. But our capacity to understand it, to measure it, to account for it, is equally vast. We are void dwellers. But we are also universe comprehenders. And that second fact is just as important as the first. Thank you for taking this journey with me through the cosmic void that surrounds us. May your sense of wonder at the universe's scale be matched by your appreciation for humanity's ability to understand it. We're in a void. We've always been in a void, and now we know it. And that knowledge, that understanding, is itself a profound achievement. One that reminds us of both the universe's vastness and our own remarkable capacity to comprehend it.